All right, this is the first of, I think, 3 or 4 integration by parts videos. So here we're just going to kind of go over the idea of the proof, and then we'll do some examples of integration by parts. So this is our first major technique for integration, with the exception of U substitution, and this kind of allows us to integrate a product of two functions. You have like the product rule, you have the quotient rule, you have the chain rule, you have all these rules for derivatives, but we don't have a whole lot for integration. And so integration by parts it can handle some products if they're in kind of a certain form. So kind of the idea of the derivation here is you let h of x be a product of two functions, f of x and g of x, which are differentiable functions. Then if we go ahead and take the derivative of h of x, so you would use the product rule. So derivative of h of x would be f prime of x, g of x, plus g prime of x, f of x. Then the antiderivatives would be equal. So we took the derivatives and we go backwards, we take the antiderivatives. So the antiderivative of h prime of x is going to be equal to the antiderivative of f prime times g plus g prime times f. And so the antiderivative of h prime would be h, which is equal to f of x times g of x. And so we have this line right here. Let me change the color. We have this line right here. And using properties of antiderivatives, we can go ahead and split that up into two integrals. Okay. And then what we can do is we'll isolate the integral of g prime of x times f of x. That's this one here. So we subtract this one over. Okay. And so there it is. Okay, and we subtract it from the f of x times g of x. Okay, so if we have an integral of the form g prime of x, f of x, dx, this gives us a formula. So usually we use the variables u and v, so let's go ahead and say u is f of x and v is g of x. So the differentials of u is du, and that's going to be equal to f prime of x dx. Differential of v dv is going to be equal to g prime of x dx. So the integral of g prime of x f of x dx is going to be equal to u dv, and making that substitution, that's going to be uv minus the integral of v du. And so here's your integration by parts. So if we can get a u dv out of that, then we can go ahead and use this integration by parts. Some of my students have come up with a saying for this one, if I can remember it correctly. So it's integral of u dv, and they say it's uv, so that'd be ultraviolet. And then the integral of v du, so the v du, they say voodoo doctor, so they say it's the ultraviolet voodoo doctor. So maybe that helps you out with remembering the integration by parts formula. Certainly one thing you can do to kind of help it stick is every time you use it, just rewrite it down. Okay. So integration by parts, if u and v are functions and have continuous derivatives, then the integral of u dv is equal to uv minus the integral of v du. Some guidelines when substituting for u and dv. dv is often the more complicated part that is also easy to integrate and will always include dx. U will be the remaining factor in the integrand. Often u will be a function whose successive derivatives will eventually be zero, such as like a polynomial. Successive derivatives of a polynomial eventually will be equal to zero. In your book, and maybe if you look up integration by parts, you might see the acronym, I'm not sure how to say it, LIAT or something like that. And that kind of gives you an idea of what you should make your substitution for u is. L for logarithms, I for inverse trigonometry, A for algebraic expressions, T for trig functions, and then E for exponentials. And so that certainly helps. I don't know if it works for every scenario, every integral, but it certainly is helpful if you need to get started. So we're going to work out two examples here, and then some more different examples in the later videos. So let's go ahead and look at the first one here. we're going to go ahead and integrate, and I think we're going to look at the integral of the natural log of x. So natural log of x dx. And so the idea of a substitution, if we're doing a u substitution, we want to replace all the variable of x with variables of u. Here, we want to rewrite the natural log of x dx as a u dv. Okay, so for the u, natural log of x in the Layet, that's like the first thing. So we're going to go ahead and say the u is the natural log of x. And the only thing left in the integrand is the dx, so we'll say that the dx is equal to dv. So then differential of u is 1 over x dx. And then v will be equal to x. Okay. So the natural log, the integral of the natural log of x dx is going to be equal to u dv. And then that's going to be uv minus the integral of v du. That's your integration by parts formula. So uv is going to be natural log of x times x. I'm going to go ahead and commute and say that's x natural log of x, minus the integral of v, which is x, du, which is 1 over x dx. And then notice that the x's will absorb in the integrand there, so you'll have x natural log of x minus the integral of dx, and that's a 1 dx. So it's going to be x natural log of x minus x, and then plus a constant of integration. And so with anything antiderivatives, you're integrating, you can always check. So if you wanted to make sure do you have the correct antiderivative, let's go ahead and take the derivative of this. So take the derivative of x ln x minus x plus the constant of integration. So that would be product rule. So 1 natural log of x plus x times 1 over x minus 1 plus 0. So that's going to be the natural log of x plus 1 minus 1, and that's equal to the natural log of x, and that's what the original integrand was. So we have verified that this is, in fact, the derivative. Okay, so I got one more here, and then if you want to look at some more examples, that'll be in the future videos. Okay, so second one here, we're going to be integrating the arc sine of x dx, okay? And so the Layet, it was logarithms and then inverse trig, and so we do have inverse trig. So we're going to let the inverse trig function, the arc sine of x, that's going to be our u. What's left in the integrand is simply the dx, so that's what we'll call dv. All right, differential of u is going to be dx over 1 minus x squared under the square root, and v will be equal to x. So now the integral of arc sine can be written as u dv. So that fits the integration by parts, so that's going to be uv minus the integral of v du. All right, so uv is going to be is going to be arc sine of x times x. Let's go ahead and commute and say that's x arc sine of x minus the integral of v, which is x, and then du is, let's see, du is, hold on a second, du is dx over 1 minus x squared. So, pardon me here, this should be a, let me fix this. This should be an dx here, okay? Du is dx over the square root of 1 minus x squared. Okay, so we're good now. All right, so then this second integral, the integral of x dx over the square root of 1 minus x squared, that's just a standard u substitution problem. So u is equal to 1 minus x squared. Differential du is negative 2x dx, okay? So to get an exact match, multiply by negative 2 and then also by negative 1/2. So maybe we do that in the next part here. Okay. All right, so we'll take the negative inside. Take that negative inside, so there it is. Okay, if we multiply by 1/2 and by 2, that doesn't change anything. Okay, so then we can see we have an exact match. Okay, so we have the x arc sine of x plus the integral, 1/2 the integral. Negative 2x dx is simply du, and then you got the square root of u on the denominator. So rewrite that as u to the minus 1/2. So then we have x arc sine of x plus 1/2, add 1 to the exponent, divide by the exponent, plus constant of integration. So we have x arc sine of x plus the square root, and then we got to be a little bit careful. What was u? U is not the arc sine. That was for the integration by parts. Now we're looking at the u substitution. So that's what our u is, 1 minus x squared, and then plus the constant of integration. So again, if you want to check, we could go ahead and take the derivative to make sure that we did find the correct antiderivative. Okay, so we'll take the derivative. So that's going to be 1 arc sine of x plus x times 1 over 1 minus x squared plus 1/2, 1 minus x squared to the minus 1/2 times negative 2x. Constant of integration goes away. So it's going to be arc sine of x plus x over the square root of 1 minus x squared, and minus the x over the square root of 1 minus x squared, 1 minus x squared. And so we're left with the arc sine of x, and so we verified that this is in fact the correct antiderivative. Okay, so I got I don't know, 6 or 7 more examples over the next couple of videos to just kind of get a little bit of experience of the different types of integration by parts problems we'll run into. Okay, so we'll see you next time.